Welcome everyone to the fourth webinar on BART. Really excited to have you and present here. I'm going to start just by showing the website really quickly. My name is John from UT Austin. So behind me on my screen, you can see the link to the BART website. And if you go to the BART website, we have there information about the toolbox, list of features and code. But at the top, we also have some of the recent events that we've been hosting, including the one today. And hopefully you've all seen this, but if you click here for more information, this will take you to the webinars page where we post all of the information. And in particular, today we'll be going through webinar 4. And the plan for today is this quick introduction, then I'll hand it off to Gopal, who will show a demo of using BART to do some of the most common operations in MRI recon. So how to make phantom data, subsample it, calibrate the maps, and reconstruct. And we have here a link to the Jupyter Notebook, as well as a binder link. This will let you run the notebook in your browser. But keep in mind that through the binder link, it'll probably be slower than if you were running it on your own machine. So we also encourage you to run it on your own machine. And after Gopal, we'll take a quick break at around the hour mark. And then we'll do a hands-on of a similar notebook where we reconstruct prospectively undersampled data that was collected on a 3T scanner. And in this case, the exercise will require you to fill in the missing code snippets. And it will be a similar process, but depending on the number of people, we might do it in breakout rooms to give people opportunity to ask more questions. So we'll see when we get to that time how to do it. And in addition, the solutions are already posted there. Please feel free to use the chat if you have questions. And depending on the size, we can even see if it makes sense to unmute. And if we're a small enough group, we'd also encourage you to just also show, if you want to show the camera as well, so that's more interactive, we'd really appreciate it too. Okay, so any questions before we get started? Okay, so I'll hand it off to Gopal, who will start with a demo of BART. Thanks, Gopal, take it away.
Thanks, John, for the introduction. Yep, so good morning, good afternoon, good evening, everyone, wherever you are. My name is Gopal. I'm a research scientist at UC Berkeley. I'm here to, as John mentioned, I'm here to speak with you all today about getting started with BART for advanced recon applications. And this is certainly not the first time that the BART team has spoken about these topics. But I have the unique perspective of having been in your shoes not too long ago. I've only been using BART for a few months. So, I'm very familiar with many of the potential pain points and they're still fresh in my memory. So, please do, I'm going to try and make this as interactive as possible. So, I'll try and stop periodically and ask for questions. And I'll be showing some of the help commands along the way and trying to make this feel more like what the program, the iterative programming environment that you might be working with as we go along. So without further ado, let's do it. I will share my screen. Okay. So yes, as I mentioned, this notebook, the basic overall idea is to demonstrate how to use BART for simple parallel MRI reconstruction. And if you're trying to run this locally, there's a few ingredients that we'll need. First, of course, is a BART installation. I'm using 0.7. You'll also need a Python 3 programming environment. And you'll also need to make sure you expose your Python 3 instance to the Python bindings within BART, which are intuitively within a subfolder called Python. So if all that is set up properly, you'll be able to run this first cell without any errors. there's also the option, as John mentioned, of running this in binder, though it'll be slower. So within this BART module, there is a eponymous function, also called BART, that enables calling the BART functions within a Python instance. By the way, you can, is the whole screen available to everyone, John?
Yeah, we see your screen, your window, and your terminals.
Okay, good. All right. So, and I'll be, showing some interactive commands along the way. So you can always take a look at what's available in BART just by typing BART and without any further flags. And you can see some of many of the functions that are available to you. Oh, it looks like we have someone who has it. Can you please mute yourself, please?
I got it.
Okay, thank you. If you do have things that you'd like to say, I think John will be monitoring the chat. That might be the best way to interact, at least not when there aren't breaks. Anyway, so yeah, so there's this BART command, and of course you can use the bash kernel to apply these commands, but we'll be working within the Python module. By the way, there's going to be some updates to the Python module very soon, so looking forward to that. And then the overall syntax is to just pass in the number of output arguments followed by the BART command and any number of arguments, input arguments that the command would receive. So for example, let's first simulate some multi-coil case-based data with the phantom command. We're setting a number of KY and KZ lines. We're setting a number of coils, and then we're calling the phantom command, which if we take a look at the help, you can always type the command followed by -H to take a look at the various options and input and output arguments, the syntax that the command expects. So you can see that -X this specifies the dimensions in Y and Z, and -S specifies the number of coil sensitivities, and it doesn't really matter what order these are in. And the -K specifies that it's going to be in K-space. And so if we run this cell, we'll indeed simulate the K-space associated with the Shep-Loebing phantom. And we can see the size right here. So I'll just pause here to talk a moment about the shape that BART arrays, BART float or complex float arrays are structured as. The dimension order, at least for a 4-dimensional array, is X, Y, Z, and then the coil number. And then a 5th dimension that sometimes arises is a maps dimension if there are more than one maps. We'll get to that more later. So you can see that by default, the phantom command produces pixels along the X and Y dimensions, but we'll be working with a sampling pattern that is feasible only along phase encoding directions. So just for clarity, we're going to reshape this to reorient our readout direction along the 0th axis. So, and after that, we can run we'll add some noise, and the noise command is BART noise. So again, the general workflow is to take a look at the various options that are available, and you can see that you can set a noise variance as well as the -N command, as well as a seed if that's necessary. I'll fix the seed for reproducibility so you can get the same exact results on your own. And so applying that to the K-space fully sampled data that doesn't have any noise, will produce some noisy K-space data. And now we can also see the result of the reshaping done in cell 3. Okay, so now we have some fully sampled noisy K-space data. the whole point of multi-coil reconstruction is to be able to reconstruct with less than fully sampled data. So it'll be more interesting to reconstruct after doing some retrospective undersampling. So that's what we're going to do next. We can construct a sampling mask, a Poisson disk sampling mask, using the Poisson command within BART. There are many, so let's take a look. Okay, so we can set dimensions of along the Y and Z dimensions, as well as a fully sampled center size. So that's what I'm doing here. I'm setting an undersampling level in Y and Z. I'm setting a dimension size at the calibration dimension. This will be more clear in a picture in a second. I'm setting a variable density factor. This controls how uniformly samples are distributed in the higher frequency regions of K-space. And I'm passing all of these arguments to BART, again, by specifying the number of outputs that we need to write to. That's the mask, the command, the various options, and then I'm also outputting the shapes to make sure that it runs, and so we get some intuition of what it's going to look like. And so take a look and see that by default, the mask shape places the samples along the Y and Z dimensions, the first and second dimensions, counting from 0. And this is consistent with the K-space shape that we used earlier. So that kind of elucidates why I reshaped earlier on. Okay, so now we have a mask, and now let's go ahead and take a look at that mask. So all we're doing here is applying the mask through a simple multiplication. This is, we'll use some broadcasting to avoid unnecessarily duplicating the mask along the coil dimension. And then I'm just going to define a simple display command, a display function, so that we don't need to repeat, because we're going to get the same, we're going to need to look at things again and again. So what does that mask look like? Okay, so now we can start to get to see some intuition as to what the various options that we chose earlier, how they influence the shape of the mask. So we can see that there are different undersampling levels along the Y and Z dimension. Y is along the horizontal axis, and Z is along the vertical axis, and it's clear that there is a higher density of samples along the Z dimension. There is a central calibration region. That's pretty typical. And then this variable density factor can be controlled as well. So why don't we just take a moment here and play with the settings to see a little bit better what this looks like. So first I'll try making this, well, let's play with that variable density factor. So if we make this 0, let this run for a second. It does take a little longer for lower values. Yeah, we can take the look. So if we set that variable density factor all the way to 0, we get something that is essentially uniformly sampled outside of the centrally sampled region. And I'm sure you can guess that if we set this to something very, very high, it's going to be highly non-uniform. So while this is running, maybe I'll pause for questions.
Yeah, Gopal, we have a quick question.
Mm-hmm.
There's a question if you can make your own mask instead of Poisson sampling.
Certainly, you can. I mean, the subsequent commands, the reconstruction commands, and can be produced using any set of commands. If you're talking about specifically using BART commands, to my knowledge, the Poisson command is for Poisson disk sampling. There may be other commands that BART provides for producing other sampling ideas. So one example I can think of is if you need to do 2D sampling, but Poisson disk only along a y dimension. I suppose one use could be to sample using the Poisson disk and only using the undersampling along one dimension and repeating that along a reduct dimension. Maybe John, I'll let you comment whether there are other commands that a user might be able to use directly from BART.
Sure, and just to emphasize Gopal's point, here we're using the Poisson tool to make a mask, but at the end of the day, it's just a 2D grid of sampled points, and you can use any 2D array you want for sampling. But in addition to the trajectory, we have the uniform undersampling or equispaced undersampling with the UPAT command, UPAT.
Thanks, John. So now this higher VDF factor has run, and we can see that in fact, with this very, very high VDF factor, that the samples are very bunched up near the low frequencies and less so along the higher frequencies. I'll set this back to what it was originally and instead play with some of the undersampling levels. I'll set this instead of 1.5 to something very high.
And Gopal, while that's running, there's another question more generally about MRI reconstruction.
Okay.
Why do we use Poisson sampling? Is it actually used in any type of MRI acquisition or reconstruction?
Sure. So the Poisson disk sampling is one way of spreading out samples somewhat randomly into KY and KZ, and that's compatible with compressed sensing reconstruction because we would like those samples to be randomly sampled. So while we could apply compressed sensing reconstruction to something that's more regularly sampled, we're going to get the best performance if we use a sampling pattern that is more random. Now, we could use a purely random sampling mask, but the benefit of Poisson disk is that a purely random sampling mask tends to bunch samples, and you can try this just by using the rand command, taking a look at the mask. The Poisson disk somewhat balances between a purely random sampling as well as spreading out the samples a certain extent. We're going to take a look at how that sampling mask looks in a second once this runs. It's going to be more clear once we further increase the acceleration factor. So here you see that with a very high acceleration factor, how this Poisson disk sampling looks quite a bit different than a pure random sampling that, if you take a look at just Gaussian noise. The samples are not placed in any particular ordering. However, there is a clear distance, minimum distance that, well, it's not a minimum distance, but more so that there is the algorithm that chooses Poisson disk sampling encourages new samples to be placed where prior samples are not, or not near prior samples. So that's more apparent in the higher acceleration factor. Okay, but for demonstration purposes, before I do that, are there any further questions? Okay, sounds good. So before we proceed, I will just return to a more reasonable acceleration factor. By the way, the reason I'm calling these undersampling levels rather than strict acceleration factors is that you can see that if you multiply these two factors, 3 times 1.5, you would expect, if this was a true acceleration factor, this would be 4.5. However, on the output, we can see that the acceleration factor is not 4.5. So this is more of an undersampling level rather than acceleration. I advise that you look particularly at this R command to the output of the the output of the command to decide what is, to establish what is your true acceleration factor, where the acceleration factor is defined as the number of samples that are taken relative to a fully sampled mask. Okay, so, and actually that will become more important in the exercise. So moving forward, we have run the default commands again. I'll just run this again so we can take a look at what that looked like. And we'll proceed. So next we're going to need to, so next, just for simplicity, we're going to run a simple FFT-based reconstruction. Sometimes this is called a zero-field reconstruction. And the basic idea is to first apply an FFT, a fast Fourier transform, along the two spatial dimensions. This produces an image along each coil, an image for each coil. And then we coil combine these images pixel by pixel by taking, there's several different ways that can be done. The one that we're going to do is just the square root of the sum of the absolute value of the square values of each of the pixels, pixel by pixel along the coils. This can be implemented in two easy steps using BART with the BART FFT and the root sum of squares commands, FFT and RSS. But before we jump to using those, it'll be helpful to just talk a bit about bit masks, because these two commands use bit masks. A bit mask is basically an instruction, a sequence of switches or bits that tell a particular function whether to operate along one of several options. So in this case, for the BART commands, a bit mask is used to specify the dimensions along which a particular operation is to operate. So the bit mask calculation can be done. So BART expects bit masks to be input in decimal representation, but it can be more intuitive and possibly also less error prone to specify the bit mask directly in binary. And we can switch between these two using the bit mask command. So that's what I'm demonstrating here. For example, we need to apply the FFT along the first and second dimensions, again, where we're starting from the 0th dimension. So that's the first is the Y dimension and the second is the Z dimension. And so we can calculate the associated bit mask in decimal representation by running the bit mask command. And I'm putting a bang here on the front so that I can run bash commands directly from a Python kernel. Okay, and so we can calculate, in fact, that a BART bit mask is 1, 2 is 6, which makes sense because 1 times 2 to the power, or sorry, 1 plus 2 to the power of 1 plus 1 plus 2 to the power of 2 is in fact 6 in decimal. So, but we don't need to do all those calculations in our head. We can just pass this, once we calculate this bit mask, we can pass this directly here in, for example, to the FFT command. Once again, the workflow is the same. If we need to use the FFT command, we go over to our command line, we take a look at what are the various options we can use to use the FFT command. Looks like we can do a unitary transformation if we need to. We need to do an inverse transformation because we're going from case space back to images. And the last thing that's expected is in fact the bit mask, and we calculated that to be 6, so I'm writing 6 here. And there's one input, the case space, and that produces some coil images. So, and the second command is just concatenating the output, the various coil images, to take a look. And what does that look like? All right, there we go. So now we have a first instance of taking a look at what the underlying anatomy of the Shek-Lowy and phantom looks like. And we can see that the various receive coils have different spatial profiles. And this is all simulated in BART earlier with the phantom command. Okay, so we'll do it one more time. Once again, using the bit mask command. This time we'll use the bitmask command to apply the root sum of squares operation along the third dimension of this sequence of coil images. Because just to remind ourselves, that's the second step to a root sum of squares reconstruction. And so again, we could calculate the bitmask in a separate step and pass it, but a more usual workflow, if we're not able to calculate this directly, is just to pass it using this this intermediate command, which is the syntax for which is to apply this $sign, and you can apply it in parentheses. So this is the syntax for running both of these types of commands in sequence. So first we calculate what is the bit mask associated with the applying it to just the third dimension, and then passing that to the root sum of squares command. Again, we can take a look at what this root sum of squares command offers. It looks like it doesn't have any options other than the health command. And in fact, that's what we're passing. So what does that look like? That's what it looks like. So we see that the root sum of squares, the zero field reconstruction, is blurry and has sometimes it's often described to have noise-like artifacts. And this is because we're not processing the coil images. We're not leveraging the redundancy across receiver coils. We're not leveraging the additional information across receiver coils as carefully as we could. So the idea of some of the more advanced reconstruction tools that BART offers is to leverage this redundancy across the receiver coils a little more carefully. And hopefully by doing that, we'll be able to improve on this reconstruction a little bit. So before I continue, I'll just pause again for if there's any further questions, because we're moving from one reconstruction method to the next.
Okay, there are just now a question, but if you have any questions, please use the chat. There's a question, where can we get the details about all the dimensions? I assume you're asking what the dimensions represent. And yes, so I don't know if, Martin, do you know where's the best place to look for that? I know that it's in the code where we have the description of the convention, but I don't know if it's in one of the doc files more accessible.
A little bit is in the README. So the basics is, I think, described in the README, and then the full explanation is indeed in the code, but in this MISC mi.h header. But you should not usually need to look there. I think the README is the right place.
Okay, so then it's also an opportunity for us to improve some of the documentation. But in general, the first three dimensions are X, Y, and Z. The next dimension is coil. And then the fifth dimension, as Gopal said, is reserved for e-spirit maps. And after that are just flexible dimensions for multiple time points and phases. The README does describe that in some basic explanation. And then there are some tools that maybe use those other dimensions, the higher order ones, for certain conventions. So we can definitely improve that. But for most cases, you probably are working with the first 5 dimensions, and Gopal will show that as he gets to the recon.
Thanks, Martin and John. If there are any further questions, I'll proceed. Okay, so we just did an FFT-based reconstruction, and now we'll move to doing something a little more clever. Specifically, e-spirit type reconstructions. So again, we'll need, so for e-spirit reconstructions, like many model-based reconstruction methods, we'll need some prior information about we'll need some additional information about coil sensitivities, received coil sensitivities. Now, certainly we could use the fully sampled center of K-space that we previously simulated to calculate those coil sensitivities. This is fine because coil sensitivities are slowly varying in space. We know that from physics. And so we don't only need low spatial frequencies to describe them in sufficient detail. And that's certainly something that's a workflow that's applied frequently in practice. For exposition, what we'll do is instead simulate some separate data that's just of the size of the calibration dimension. So in practice, this would not take very much time at all, just the fully sampled separate center, and estimate coil sensitivities from that instead. And that has, surely that has the disadvantage that, you know, we have to do a little more acquisition if this was real data. However, there is the advantage that now the resulting sensitivity maps would be uncorrelated with the K-space at the time of doing the model-based reconstruction, which is really what the model with which the reconstruction is developed expects. So once again, we'll apply the Phantom command to simulate some sensitivity map data. That's why I've labeled it associate accordingly. And instead of simulating for the entire NKYZ, we just need the calibration dimension, which is tiny. You can see that earlier it was 16. There it is. So this is a very small matrix, very small array. And we'll set a different C to make sure that this data is uncorrelated with the prior data. And again, we'll add noise, nothing new here with the noise command. So again, just running a couple of commands in sequence here to start to look like what this is going to look like. The workflow is going to look like more like in practice, simulating some phantom data, adding some noise. And then I always take a look at the shape just to make sure I know what's going on. And in fact, it's only 16 by 16 by 8. Okay, so the BART-Toolbox offers the eCalib command to estimate coil sensitivities from low frequency data. And specifically, it calculates coil sensitivities as described in the eSpirit method. And you can check out the original paper if you'd like to learn more about the details of the sensitivities as well as the reconstruction. So presently we see that this data is only 16 by 16 in the spatial dimensions. We'll need to estimate coil sensitivities with the same pixel width that with which we'll be applying them in reconstruction. In other words, the coil sensitivities will dictate the resolution at which we reconstruct images by default. And so one way to do this is to zero pad the sensitivity map K-space data before proceeding. So this is very easy. Anybody who's tried to use the NumPy's pad command knows that it can be somewhat cumbersome in NumPy. BART makes this very easy with the resize command. Simply specify the dimensions along which you'd like to resize. We need to resize along the first and second dimensions. And the C command, so I'll take a look again. All right, so the -C command specifies that we want it to be, we want to resize such that the original data is in the center. And we want to output that, one output of that to the padded K-space. So that's what I'm calling K-space S sensitivity map pad. And we'll run that, and as expected, we've now expanded along the K-space spatial dimensions. All right, so now we have zero pad K-space data. and we're ready for sensitivity map estimation. We could go ahead and estimate sensitivity maps right away. However, we can reduce the computation of both the sensitivity map estimation as well as the subsequent reconstruction by first compressing the coil data into a smaller number of virtual coils, is the typical name. And so BART has the CC command, coil, which stands for coil compression, to assist with this. And there's actually several algorithms that are available. Let's take a look at what BART offers.
Paul, sorry to interrupt. There's a question if you could make the Jupyter Notebook text a little bit bigger to zoom in.
Sure.
Thanks.
How does that look?
Looks good.
Okay. So where was I? Right, I was mentioning that the coil compression command within BART has actually several coil compression algorithms. We're taking a look at the help to see what some of those algorithms are. There's SVD type coil compression. That's basically where you take a SVD along the coil dimension, where you collect the spatial dimensions along one dimension and the coil dimensions of the other, and basically compress using the singular value decomposition. There are some more tailored methods like geometric GCC, geometric coil compression, as well as E-spirit type coil compression with -E. We'll use the SVD type compression here, and I encourage you to try some of the other flags and see how things change. Okay, so we could go ahead and apply this CC command and go ahead and output directly some compressed K-space data. However, there are many virtual coil orientations that are equally good for any given geometry. For example, the SVD is invariant up to a rotation. And so to make sure that we use the same virtual coils to make sure that our virtual sensitivity maps that are estimated match with the compression that we apply later to the K-space data, we want to make sure that we use the same coil compression matrix. So BART has this alternate option of instead outputting the compression matrix rather than the K-space data, the compressed K-space data. And so that's what we're doing here. We're using not only the -S command for SVD, but we're also using the -M command to instead output the compression matrix. And we're saving that into the coil compression matrix command. Specifying a number of virtual coils. We originally had 8 coils, so I'm compressing to 5. Go ahead and try different numbers of coils if you'd like. And so now, once we have this coil compression matrix, we can apply it using the CC apply command, the coil compression apply command. You can guess what I'm going to do. I'm going to take a look at how to use it. It looks like we can specify the number of virtual coils using -P, as well as the type of coil compression that we had, that the coil compression matrix is with -S. And this command takes 2 inputs: the original 0-padded K-space as well as the coil compression matrix, and it outputs some compressed K-space data. And so now we can more clearly see what I was talking about in making sure we apply the same coil compression matrix to also compress the original K-space data with which we're going to do reconstruction in the same way, with the same coil compression matrix. So now we have these two new variables, compressed date variables, K-space sensitivity map coil compressed, as well as KSP coil compressed, that have the same, that correspond to the same coil compression matrix. Okay, so Let me make sure I run those. Okay. And we can see that the result of this cell is that the dimension along the coils has reduced corresponding to the number of virtual coils we requested. And we'll take a look at what the results on the coils, the coil estimates are in a second. We'll apply the same thing to the original case-based data and again compress it. Okay. All right, so we're now ready to estimate coil sensitivities. BART enables this again with the eCalb command. And let's take a look at what that command looks like. Okay, it has a few options. By default, the eCalb command outputs several sets of sensitivity maps, specifically more than one sensitivity map for each coil. This has some relevance if you're trying to do things like separate fat and water where there could be shifts. In this situation, we don't have anything, we don't have chemical shift or anything so fancy, so we just need the first set of sensitivity maps. And so I'm using the -m followed by 1 to specify that we only need one set of sensitivity maps along this sensitivity map dimension. And as John mentioned, that will be the fourth dimension, counting from 0 again. So let's go ahead and run the eCalb command and see what happens. The second command again just displays after concatenating along the coil dimension. All right, it runs quite quickly. And here we go. Here we have some coil sensitivities, and you can see that these coil sensitivities don't quite, they don't necessarily align with the coil sensitivities that we see visually originally because we first coil compressed. I encourage you to skip the coil compression step, and you should in fact see that the coil sensitivities, while there will be more of them and therefore the reconstruction will be longer, they will align with the original, the coil sensitivity that we can see visually here. But we're working with virtual coil sensitivities, and this is the eCalb command chose to structure them in this way. All right, so we have sensitivity maps. We have undersampled case-based data. So we're now finally ready for iterative reconstruction. I think this is a good spot to potentially stop again and ask for questions. John?
There have been a few questions in the chat that we've been answering as we go. I think the main one was about resize, and resize can do both zero padding and cropping, depending on whether or not you give it a bigger or smaller dimension. And that's all it can do is zero pad and crop. It can't do any other kinds of interpolation.
Okay. Okay. Sounds good. So we'll go ahead and talk about reconstruction. So we'll be focusing on the PIX command. PIX stands for parallel imaging and compressed sensing. And the PIX command enables eSpirit reconstruction. Again, if you want to learn more about the details of eSpirit, I encourage you to check out the paper that I linked earlier. And so we should definitely take a look at the help with PIX. And there's quite a bit to look at. So let's take a look. PIX is very versatile. It enables multiple types of regularization, which is, improves upon, helps in iterative reconstructions improve in the case of undersampled data like what we have now. It also enables multiple types of optimization algorithms. So you'll see when we run it later that some of them use things with inner iterations. There are other types as well. There's a soft thresholding. There's also a basis pursuit formulation. So it's quite flexible in that way as well. We'll just focus on a particular couple settings within the regularization command. And so that's what we'll talk about here. In fact, the regularization command has its own set of options that we can take a look at using as the instructed RH. So let's take a look at that too. Might actually, yeah, let's take a look at that as well. So there are many regularization options as well that are listed here. So a lot of the information is listed right here, but I'll talk about it here as well in case there are questions. The regularization flag is specified with several arguments. First, regularization type. We can see that there's quadratic regularization, there's image domain L1 regularization, wavelets, hard thresholding, et cetera, et cetera. Then the next argument, which I'm calling A, which is consistent with over here, it's a bit mask, and that bit mask denotes the dimensions along which to apply a transform, typically a sparsifying transform, if the associated method needs it. We'll talk about that more in a second. The second argument, which I'm not going to speak about in great detail, is the dash B, the B argument. That is a bit mask that denotes the dimensions along which to apply joint regularization if that's needed and if that applies to the associated type of regularization. And again, none of the examples that I'm going to show here in this introductory exercise are going to talk about that. But we will need to specify the strength of the regularization, and that can be done with the third argument. Generally speaking, using more regularization encourages the reconstruction to look more like what the image model that the regularization encourages, unsurprisingly. And if we reduce this strength, we get something that's more consistent with the data, though there may be more noise-like artifacts in the reconstruction. Okay, so there's also another flag that we're going to use, the dash S. This warrants some discussion. Let's go back up here. Right, it's right here. So, and this is to it concerns rescaling. So, if we don't use rescaling, then the images, the reconstruction algorithm for a given regularization parameter is not going to be invariant to rescaling of the data. And the reason is obvious. If you double the values of the data, but you don't double the value of your regularization parameter, then the effective strength of the regularization parameter to first order halves. So this dash S command eliminates that concern in that the data is rescaled, it's normalized in a way that, so that regardless of what the scanner output, the regularization parameter is going to have the same influence on the reconstruction as if it had been doubled before being passed. Now, that's done by default. If we don't pass the dash S command, then the images won't be scaled back for output, which can be, so if it's going to be if you want to put them all in the same color bar at the end, like we do at the end of this demonstration, they could have different scaling factors. You don't have to worry about this if you use the dash S command. You'll just basically undo that scaling, which is used to control regularization. So with the dash S command, we'll have invariance to scale of the data, and we'll also get back images on the same, with the same units, the same range of values that we would have if we hadn't applied the scaling. This is a little bit of a detail in this situation because we're, the BART is able to do this on the, by itself, the scaling by itself, because we're passing a fully sampled center. In the exercise, we won't have that available. And so this there'll be more discussion about this flag, and we'll have to choose that scaling manually. And so stay tuned for that and take a look at that in the exercise. Okay, so we talked a lot about options. So let's try running the PIX command in a few different ways. Okay, first we'll do a very simple quadratic regularization. So the BART command has one output. We call the PIX command. We specify the regularization. We specify that we're using regularization with the -r command. We can see that, where did I write it? Oh yeah, okay. To specify a quadratic or L2 norm regularization, we use the Q, and the Q only requires the third regularization strength, as there is no transform. It's done in the image domain. So we pass that, so a regularization strength. And we can go, and so this receives two arguments. All of these receive two arguments: the Coil compressed case space data, as well as the sensitivities. We'll go ahead and run that. All right, here we go. So a little bit sharper than the root sum of squares reconstruction. However, maybe we can do a little bit better with a different type of regularization. So we'll next run PIX using L1 norm regularization. So L1 norm regularization tends to produce sparsity in the associated basis along which you apply the L1 norm. In the case of the wavelet domain, the wavelet transform, we're encouraging sparsity in a wavelet domain. Okay, so this is a situation where there is in fact a transform, so we need to specify that first flag. We want to apply the wavelet transform along the two image dimensions, and recall that the image dimensions are the first and second dimensions. So I'm going to avoid binary math and just go ahead and let BART do the hard work and ask it to compute the associated bit mask. I'm going to specify the wavelet transform. And okay, we're also using this -d5 command because that's D stands for, we can take a look here. Nothing special. It just describes a debug level. You can try playing with different debug levels. The fifth debug level gives a little more output for us to take a look at. And in fact, when we ran the L2 norm regularization, we saw what the scaling factor was. We saw that it used a CG conjugate gradient algorithm. We made sure we could have verified, in fact, that we set the regularization to 0.1, and we can see the value of the cost reduce over a set of, by default, 30 iterations. And it also tells us the amount of time that it took. I think that would be in seconds. Okay, so where was I? All right, so we have set, so this is the command looks very similar to before. We're just setting now also the sparsifying transform dimensions, again a regularization strength, otherwise the same flag. So we'll go ahead and proceed. And we can see that the resulting reconstruction is a little better. Why is it better? Well, where the regularization more aligns with what we want the resulting image to look like. We would like sparsity in a wavelet domain. We would like sparsity not, well, first of all, we'd like sparsity. That's what is being encouraged with the L1 norm rather than the L2 norm. And we don't necessarily want to regularize in the domain of the image. We don't necessarily want to suppress the values of the image, but rather we want to suppress variation in the image. And one way of converting from an image domain to a variation in image domain is using the wavelets. And so the resulting reconstruction, it looks a little bit better. And let's take a look at the output of the algorithm. So we can see the scale. Yeah, we can see the scale factor. We can see that rather than running conjugate gradients, it ran fast iterative self-thresholding algorithm, or FISTA. Many papers about this if you'd like to learn more. Feel free to ask questions later in the exercise if you'd like. Again, we're running it for 30 iterations. We see that the cost value is descending over time, which is good. In fact, it's descending, should be descending. Yes, it's the cost funding, generally speaking, is descending over time. And it took still less than a second. So, and we could have played, let's try, go ahead and change the number of iterations. All right, so I'm doing something dangerous here. I'm just trying something on the fly. Okay, what happens if we run this at 50? All right, in fact, it runs for 50 iterations, and the cost value, did it change specific? There was a little bit of a change, less than a 1% change relative to running it for 30 iterations. So it looks like the default number of iterations we ran was okay. Okay. All right. And finally, let's try running picks with total variation regularization. So we can also apply the L1 norm using a different sparsifying transform. That this transform could be the first differences. In the case where the first differences are taken in all of the spatial dimensions, which it is in this case, that first differences is called total variation. And so that's what we're doing here. The only thing that's different is that instead of choosing a wavelet transform, we're using total variation transform. We're specifying the same dimensions along which to apply it, and otherwise the flags are the same. So it's quite consistent. And actually, yeah. So we can go ahead and run it. Maybe we should run it for 50 iterations for consistency. Okay. Looks like it still took under a second. This is a 2D problem, so keep that in mind. And well, there you go. It looks, the image looks a little bit, maybe a little less variation in the regions that we know the Shep-Logan phantom is supposed to be smooth. And this isn't too surprising. One of the features or drawbacks, depending on your point of view, of total variation regularization is that it tends to produce piecewise constant images. So if your anatomy is piecewise constant, you're going to get an image that what you expect. So there you go. That's the reconstruction. And let's take a look at them side by side. No new commands here. We're just applying again, a root sum of squares reconstruction, but using the fully sampled data that wouldn't have been available in practice, just for reference purposes. What should it have looked like if there was fully sampled and if there had been no noise? And we'll do a root sum of squares of that and look at that side by side. Maybe it'll help if we take a look at this nice and zoomed up. We can see, in fact, like I was saying, that the total variation regularization gives something that's reflects what the underlying anatomy was, but keep in mind that it was kind of destined to do well on this piecewise constant problem. And we'll take a look in the exercise which of these does best or is able to do best with real data. And that pretty much sums up what I have. Looks like we're just at the hour mark. So I think it would be okay to take a couple questions, but we should take a break soon and move to the more interactive portion. John?
Thanks so much, Gopal. That was really great. And we did have a bunch of questions. They mostly got answered in the chat. They were about coil compression and some things related to eSpirit. So I encourage you to look at the chat to see those answers and also ask additional questions. So really quickly, are there any other questions before we take a break? Okay, there is a question kind of specific to eSpirit. what is the advantage of using higher number of sensitivity maps in the reconstruction? I think, Gopal, you touched on that earlier. Maybe you could just say it again.
Yeah, I'm certainly not an eSpirit expert. I think we have eSpirit experts on the calls, so I'll let them comment. But one application that I know of is where the higher order sensitivity maps can provide information when there are shifts that arise due to the chemical shift, the phenomenon, the non-ideality of chemical shift, which we don't have in this situation. Chemical shifts can cause a shift in, or chemical shifts are due to the fact that in the simplest case, fat and water have slightly different resonance frequencies. So if you reconstruct an image using linear gradients, you get a linear shift in the image of the fat relative to the water. This can cause overlap, and this can be captured to some extent with the higher order sensitivity maps. I am not an expert on that, on how eSpirit does that, so I will let Martin comment.
So I can also just comment and mention that or it looks like Mickey wants to say something. Go
Yeah,
ahead.
I just want to say that actually one of the main applications for the other sensitivity maps, if your calibration region field of view doesn't support the entire object and there is some aliasing in the calibration region, just using a single sensitivity maps can now be represented by a small like a smooth map because of this aliasing. And so the second sensitivity map actually helps in mitigating artifacts that don't appear in the middle of the image. So there's a really nice paper by Griswold showing how Grappa can deal with this type of small field of view map calibration area compared to Sense that uses a single sensitivity maps that cannot. But eSpirit basically solves this problem by using two sets of sensitivity maps. And that's really I think the main thing that people would see when they use eSpirit. The other one is if there's any data consistency in the calibration region due to motion or, as Gopal said, chemical shift, then that second sets of sensitivity maps helps mitigate with that.
Thanks, Mickey. Very clear.
And also the eSpirit paper has really nice figures that show all three of those cases. So it's a great place to look. Okay, there are a few other questions coming in, but in the interest of time, why don't we take a 5-minute break and we can start back up a little bit more than 5 minutes. We'll start back up at 10 after. For the next part, we'll also likely go into breakout rooms so that it's a smaller group and easier to ask questions. But we'll go ahead and stop here. Thanks so much again, Gopal. That was a really excellent introduction.
It was a pleasure. Have fun.